Hello, everyone. Thank you for joining today's webinar titled The Vero Interferometric AFM, Improvements in Accuracy and Precision. Today, we will hear from two speakers. Ben Oler is the Senior Product Line Manager for the Cypher, Jupiter, and Vero families of AFMs at Asylum Research. He received his PhD in chemical engineering from the University of California, Santa Barbara. He has worked as an application scientist and in product marketing in the AFM industry for the past 23 years, and for the last 10 years at Asylum Research. Jason Lee has more than 2 decades of AFM experience and graduated from Stanford University with undergraduate and graduate degrees in mechanical engineering and materials science and engineering, respectively. He joined Asylum Research more than 20 years ago and has been involved with many aspects of the business throughout his career. Before we begin the presentation, I would like to cover a few webinar logistics. All attendees will be muted throughout the webinar, but we welcome your questions. Please submit your questions using the question section of the GoToWebinar interface. You can submit them at any time, but we will answer them at the end of the presentation. If you are directing your question to a specific presenter, please include that speaker's name with your question. We will address as many questions as possible at the end of the presentation. If you have any connection issues, please be aware that we will record the webinar and you will be able to view it at a later date. With that, thank you again for attending the webinar. I would now like to pass the controls to our speakers.
Hi everyone, I'm Ben Oler. I'm the Senior Product Line Manager at Oxford Instruments Asylum Research. Thanks for joining our webinar today. It's my pleasure to welcome you to our second webinar introducing our new AFM, Vero. In the first webinar, we introduced Vero and we focused on its exclusive quadrature phase differential interferometer technology. In today's webinar, we'll repeat a lot of those same topics in case you missed the first webinar, but this time with more focus on how that QPDI technology improves measurement accuracy and precision. I'll be providing an introduction to Vero and QPDI and how they contribute to measurement accuracy and precision, and then hand off the webinar to Jason Lee, who will further describe these benefits and illustrate them with examples. So let's get started. Vero is our next generation AFM from Asylum Research. It joins our MFP3D, Cypher, and Jupiter AFM families. What's new and unique about Vero is that it's the first and only AFM to use quadrature phase differential interferometry to produce more accurate and repeatable results. And that's where we'll focus in today's webinar. But it's also important to note that Vero builds on the ultra-high performance, stability, and capabilities of our Cypher AFM family. That means that Vero is an ultra-high performance AFM that supports a full range of modes and accessories and can therefore be applied to virtually any field of research. You probably all recognize schematic drawings like this one, which illustrates how AFMs sense cantilever motion. It goes by various names: optical beam detection, optical beam deflection, optical lever detection, and beam bounce detection. It doesn't really matter what you call it, but we'll call it OBD. It uses a laser reflected off the back of the cantilever to measure the angular deflection of the cantilever. The vast majority of AFMs made in the last 35 years use this approach, and while many other aspects of AFM design have evolved and improved over the years, at Asylum and pretty much every AFM company, we've kept using this same basic OBD technique. In fact, unless you've been doing AFM for a very long time, OBD may be the only method of cantilever sensing that you know about. But if you look back to the very beginning of AFM, those early AFMs didn't use optical beam detection. Believe it or not, the very first AFM by Binning-Quaite and Gerber used scanning tunneling microscopy to measure the cantilever deflection. That made sense given that the AFM derived from their invention of the STM, but other groups soon developed more practical alternatives. One of those alternatives was interferometric cantilever sensing. But those early interferometric AFMs suffered from some practical limitations too, as I'll discuss next. So when OBD was developed in 1988, it rapidly displaced these other techniques. There were a few holdouts here and there for specialty applications, but OBD became ubiquitous in most AFM designs. So why were those early interferometric designs so rapidly abandoned in favor of optical beam detection? Well, not only were they complicated to design, build, and use compared to OBD, but their performance was also not that good. Most were simple Michelson interferometers, so they could only measure displacements much smaller than the wavelength of light. That's because they had to operate on just a small fraction of the sinusoidal interferometer output, where the signal has good sensitivity and is approximately linear. Those early designs were also subject to lots of drift and low frequency noise because the reference mirror of the interferometer was placed far away from the cantilever, resulting in a very long optical path. More recently, here at Asylum Research, we have ourselves offered an AFM that included interferometric sensing. We called it the Cypher IDS, where IDS stood for Interferometric Displacement Sensor. Specifically, the Cypher IDS was a cipher where a third-party laser Doppler vibrometer was integrated into the laser path by using the beam steering optics that we normally use for our blue dry photothermal excitation option. The Cypher IDS was sold specifically for piezo response force microscopy measurements, and it was great for PFM and well adopted by some of the leading researchers of piezo and ferroelectric materials. In fact, that success is one of the things that motivated us to develop QPDI and Vero. That said, the Cypher IDS also had a few big disadvantages. The big one is that the IDS signal could only be used for high-frequency measurements. The reason is that the IDS used a vibrometer, which measures velocity. Only by integrating the velocity do you get displacement. So at low frequencies where that velocity is very low, the noise and drift of the displacement signal was much higher. That meant that we couldn't use the IDS signal for force curves, fast force mapping, or any other technique requiring a DC stable displacement signal. It was also not compatible with our blue dry photothermal excitation option, since we essentially hijacked those optics to introduce the vibrometer beam. And finally, while the IDS offered lower noise compared to optical beam detection, it was not as low noise as what we've now achieved with QPDI on Vero. So in short, the Cypher IDS was limited to mostly PFM applications. But we knew that interferometric sensing would be very powerful for other techniques if we were able to address those disadvantages. So that's what we've done here now with QPDI. The patented Quadrature phase differential interferometer technology that we've developed for Vero has eliminated all of the shortcomings of both those early interferometric AFMs and the Cypher IDS. QPDI is now easy to use, it directly measures displacement instead of velocity, and its performance is now dramatically better than optical beam detection. These improvements come from two unique features of QPDI. First, it's not a basic Michelson interferometer or a laser Doppler vibrometer, but rather a quadrature phase interferometer. That means that it generates two interferometric signals out of phase with one another. So at any given time, one or the other will have optimal sensitivity, and we can track the outputs over multiple wavelengths. The benefit is that QPDI can measure very large displacements and do so while maintaining very low noise. Second, it's a differential interferometer. That means that instead of placing the reference mirror far away from the cantilever, we're now using the back of the AFM probe chip as that reference surface, less than 1 millimeter away from the cantilever. This results in dramatically lower drift and far better low-frequency noise performance compared to typical interferometers. QPDI provides several major benefits over optical beam detection. First, the most fundamental benefit, which is that QPDI measures true vertical tip displacement. Second, QPDI improves measurement sensitivity by measuring the tip displacement with often over 10x or better lower noise compared to OBD. Third, QPDI avoids crosstalk between vertical and in-plane tip forces, which affects the optical beam detector signals. And fourth, the QPDI is precisely calibrated by the wavelength of light, which makes the displacement measurements very accurate. All of these things add up to enable Vero to produce more accurate and repeatable results. Jason is going to be showing you examples of many of these benefits, but before I hand things over to him, I want to take a couple minutes to explain this first, most fundamental benefit of QPDI. So what does it mean that we measure true tip displacement? You might be thinking to yourself that all AFMs can measure tip displacement, but that's not true. We've all been using OBD on AFMs for so long that we don't think about what OBD really measures, and more importantly, what OBD can't measure. OBD measures the change in the angular deflection of the cantilever. But in most AFM measurements, what we really want is the tip displacement. But instead, we're stuck measuring this angular change in the cantilever and trying to relate that back to tip displacement. The idea is simple. If the tip is displaced, the cantilever will bend. But as I'll show in the next slide, there are cases where changes in the cantilever angle don't correspond to tip displacement. In retrospect, it's surprising that we've used this indirect measure of tip displacement for all these years. And that's what QPDI does differently. QPDI is an interferometer, so it measures displacement. Therefore, if you place that interferometer spot directly above the tip, then you're directly measuring the tip displacement. And that's why QPDI is such a breakthrough technology. For the first time, we have an AFM, Vero, that can directly measure what we really intend to measure, which is the motion of the tip and not the angle of the cantilever. You might still be asking yourself, why is this distinction between the cantilever angular deflection and tip displacement so important? The problem with OBD is that all cantilever bending is interpreted as tip displacement. The OBD method can't determine why the cantilever is bending. One of the first places that we notice the consequences of this problem is with piezo response force microscopy. In PFM measurements, there's often an electrostatic force generated between the sample and the cantilever that can excite the cantilever resonance. OBD sees that cantilever bending and misinterprets that as tip displacement, even though the tip itself isn't moving. This is the origin of a common artifact in PFM measurements. But as we worked on that problem, we came to appreciate that this issue affects other measurements too. In contrast, when you use QPDI, it only measures displacement. So again, if you place that spot directly over the tip, then the cantilever can still resonate and bend, but since the tip itself is not moving, that does not affect the QPDI signal. So not only do we get a much more accurate and sensitive measurement of the tip displacement, but we also avoid those artifacts associated with erroneous interpretation of the OBD signal. Since Jason's going to be talking about how Vero and QPDI improve measurement accuracy and precision, I thought it'd be helpful to briefly review what we mean by those terms, because not everyone uses them consistently. An accurate measurement is one where the average of the measured values is the same as the true value. That's shown here in the two examples on the left, where the distribution of the measurements are all centered around the true value, which for illustration here is 0. Good accuracy requires the elimination of systematic measurement errors. Precision is something different. Precision refers to how tightly that distribution of measurements is clustered around one value. Often this is expressed as the standard deviation of the measurements. You can have accurate measurements that lack precision, you can have precise measurements that lack accuracy, and you can have measurements that are neither accurate nor precise. But obviously what you really want is both. You want an accurate and precise measurement. So how do we think about this in the context of AFM? There are many factors that influence the accuracy and repeatability of AFM measurements. To help appreciate how QPDI will affect those, I thought it might be helpful to start with a more familiar example. If you look back at the early days of asylum research, we pioneered the use of closed-loop X, Y, and Z scanners. Closed-loop scanners use position sensors in the scanner to correct the inherently nonlinear and hysteretic motion of the piezos and enable more accurate measurements of sample topography and sample properties. All asylum AFMs use closed-loop scanners, and most, but not all, of our competitors have followed along and adopted that technology too. Now, alongside the development of the scanner, Asylum also pioneered the development of very low noise displacement sensors for use in those scanners. The lower noise of the sensors improves the measurement precision, which in this case improves imaging resolution. Asylum still maintains this performance advantage versus our competitors because of our unique patented low noise LVDT sensor technology. Today, it'd be almost inconceivable for an AFM company to release a new AFM that had an open loop scanner or noisy sensors. Those technologies have just become expected in any modern AFM. But scanner accuracy and precision is just part of the story when it comes to overall AFM measurement accuracy and precision. So how will QPDI improve AFM measurement accuracy and precision? Well, the cantilever sensing system of an AFM contributes its own sources of errors too. The difference is that those errors are a little more subtle than those that come with an open loop scanner. If you use an open loop scanner, you really know it because whenever you change the scan size or scan offset, you see these huge distortions in your images that take many scan lines to settle out. Using a closed loop scanner is really a night and day difference because that obvious scan artifact just goes away. But just because the cantilever sensing errors are less obvious doesn't mean that they're less serious. OBD cantilever sensing introduces both systematic and random errors that have detrimental impacts on many different types of AFM measurements, especially as we push AFM to provide more quantitative analysis of sample properties and not just qualitative image contrast. Here are a few examples. In piezo-response force microscopy, there are often serious artifacts caused by electrostatic interactions between the sample and the cantilever, as I described previously. Those electrostatic forces affect cantilever bending, which OBD misinterprets as tip displacement. In force measurements, in-plane forces as the tip slides across the surface causes buckling of the cantilever, which OBD misinterprets as part of the normal or vertical force being applied to the sample. There are also systematic errors in the calibration of the invols or deflection sensitivity and the cantilever spring constant, which can be major sources of inaccuracy. Now, there are also corresponding random errors from OBD that also affect measurements and affect the measurement precision. The noise in the OBD deflection signal often sets the lower limit on the sensitivity of many measurements, and there's a complex influence of the choice of cantilever on that noise. There are also random errors that affect the invols and spring constant calibration, which is one of the reasons that it's often difficult to compare AFM force measurement data sets that were collected with different cantilevers. But when you replace the OBD cantilever sensing with QPDI, all of those benefits of QPDI that I outlined either eliminate these errors or dramatically reduce them. Since we measure the true vertical tip displacement and we avoid crosstalk between in-plane and vertical forces, those measurement artifacts are dramatically reduced. The fact that the QPDI is directly calibrated by the wavelength of the laser eliminates the invols calibration and makes spring constant calibration far easier and more accurate. QPDI is much lower noise than OBD, and the noise is no longer a function of the cantilever size, which greatly improves measurement sensitivity and precision. And since there's much less to do in terms of calibration, most of that variability between measurements goes away. A lot of these errors are ones that have been kind of hidden because they affect all AFMs that use OBD, which is pretty much every AFM sold for the last 35 years. Certainly, there have been some groups trying to chase down and correct for these errors, but real solutions have been elusive, so most AFM users have just accepted them or have simply remained unaware. But just like closed-loop scanners made us all more aware of open-loop scanner artifacts 20 years ago, now QPDI is going to help shine a light and uncover these OBD artifacts, and undoubtedly uncover more of them that we haven't realized yet. So thank you for your attention. I'll turn the webinar over to Jason Lee now, who will take us through some actual examples of these improvements to AFM measurement accuracy and precision. Thank you.
Okay, thanks Ben for that very nice background on QPDI and the introduction to our Vero AFM. You know, what you said just now really resonates with me as a fellow AFM user for many years now. We do become sort of blind or at least resigned to the limitations of our current scientific instrumentation sometimes, and it's not until you have really significant improvement like this with QPDI that you can sort of have the perspective to reflect back on what has been and really how good things are now with QPDI. And I find myself, you know, in my day-to-day when I image, often choosing Vero for its improved accuracy and precision. And that's what we're going to focus here in this part of the webinar, is really talking about the improvements of Vero QPDI in terms of accuracy and improvement. So we like our acronyms in the AFM world here, and here's two more, right? OBD and QPDI, and you already heard this a little bit from Ben's part, but I want to make sure that we cover this before we move on, because we're going to be doing a lot of comparisons between OBD and QPDI. So OBD stands for optical beam deflection. This is how your AFM in your lab works. All commercial AFMs out there use OBD, this detection scheme, and it's measuring angular changes of the cantilever. So you can literally think of it like a little protractor, like I've represented there. But this angular change we don't actually care about. What we really are after is the tip displacement, meaning how far did that tip move in the vertical direction. And so you need, with OBD, some conversion value, which we call invols. This stands for inverse optical lever sensitivity. Sensitivity being the key word there, to convert between an angle and an actual tip displacement. Now, this factor is dependent on many different things like spot size and spot position and the cantilever length. And so there can be some uncertainty and error just from that alone. But the other perhaps more important point, which you'll see in the later coming slides, is that there can be angle change with no tip displacement. So the problem with OBD is that because it's looking at angular changes, we can't distinguish between what's a real angular change that's due to something that we're trying to measure and an angular change that's due to just an artifact or some other phenomena. And so OBD will just look at the angular change and say the tip displace, a certain amount corresponding to whatever that angle change happens to be. Now, QPDI, of course, stands for Quadrature Phase Differential Interferometry. And this is sort of like having a nanometer scale ruler. We have this calibrated to the wavelength of light that we use, and it's measuring tip displacement directly. So this is great, right? This is what we're after. And unlike with the OBD measurement, where we're really inferring the tip displacement through something that we can actually measure, which is the angle. Whereas now with QPDI, we can just directly measure the tip displacement. So there's less that can be lost in translation when you're converting from one thing to the other. All right, so with that, you've already seen a little bit in Ben's part, but interferometric AFMs are not a novel concept, right? Especially directly after the advent of AFM, there was a flurry of activity. Many groups were looking at various detector options, and certainly some groups were looking at interferometric AFM. This is from 1987. In 2018, we launched the Cypher IDS, which took our Cypher AFM platform and integrated it with a third-party vibrometer interferometer. And building on the success of this and the interest, we launched the Vero AFM at the fall MRS conference this year. All right, so let's talk about accuracy. We named Vero after the Latin root ver, meaning truth, because in part, Vero will give you the truth. It's insensitive to a lot of these effects that cause error in the measurement. One of the really nice things about Vero is that we have a built-in nanometer scale ruler, and this can be great for many things, one of which is spring constant calibration. So with OBD, if you had a spring constant calibration that was within 10 to 20% of the true value, that was deemed pretty good. That was, sort of typical of what you could achieve with OBD. Lots of potential sources of error there in that measurement. With Vero now, that we have this interferometer that's tied to the wavelength of light, we can dramatically reduce this error. And so what we did in this measurement is we took a series of these NIST pre-calibrated cantilevers and a varying spring constant or varying stiffness, and we just measured with Vero what the spring constant was calculated to be for each of these levers, and then we just plotted one versus the other. So if everything were perfect, it would be a slope of 1. Well, we had a slope of very close to 1, right? And this becomes the error in the measurement. So these cantilevers spring constants were agreed to the NIST SI traceable values to within 1%. It's pretty incredible to have something like that just built directly into the AFM. The other thing that can affect the accuracy in measurements is, again, and I alluded to this in the first slide, is that whenever the cantilever has bending or buckling that's not related to the actual tip displacement, that can look like real signal when in fact it's just an artifact. So we can see this in a force curve, and I'm showing two force curves here on the right. The one in red is OBD, and the one in blue is showing the QPDI data. It's the same cantilever on the same sample, and one curve has just been offset from the other so that we can see both curves. And if you're not familiar with what a force curve is, we're simply starting with cantilever off the surface, as you can see in the diagram on the left there, and keeping track of the Z position as we ramp towards the surface and monitoring the cantilever's displacement or deflection signal, which we plot there on the vertical axis on the plot. So in this particular case, we start with cantilever off the surface, and I've shown that as position number 1 here. If we move towards the surface, then there's no change in displacement or deflection because the tip is not interacting with the sample yet, and so there's no change. Right when we touch down on the surface, we're in this linear regime, as you can see here, represented in this brown cantilever and spot number 2. And then if we apply even more force, we see something interesting happen. Of course, the tip sample friction will be commensurate with the loading force, and we can see the cantilever actually start to buckle. And so we get sort of this additional curvature in the cantilever that's independent from what the tip displacement actually is. And this, slope would actually underestimate what the actual tip displacement would be, right? And so here at position 3, we start deviating from what the actual displacement should actually be with OBD. With QPDI, you see that we're still on the linear regime here, as we should be. Then when we retract the probe, the cantilever shape bends a different way, and that would overestimate the displacement or deflection. So with OBD, we get this sort of hysteresis between the extend and the retract. So when we extend, it's the solid line, and retracting is this dotted line here. Let's zoom in a little bit so we can see a little bit better what's going on. And here we can see, again, the extension in brown, and the cantilever shape sort of curves this way. And then when we retract the probe, the cantilever bends the other way. And this curvature, again, will cause the hysteresis that we see with OBD. But the tip position remains the same. And so as we do the force curve with QPDI, this displacement changes linearly, whether we are in the extend or the retract portion. So, of course, tip sample friction is still there. The cantilever is still bending, and there's this curvature even when we measure it with QPDI detector, but the QPDI detector is not sensitive to it. So there can be a few different phenomena that affect the cantilever bending, like tip sample friction. Another factor could be electrostatics between the cantilever and sample. And then the third factor would be in-plane response of the sample affecting the measurement. And I'm going to give you a quick overview here of piezo force microscopy, because with this technique, you can actually observe all three artifacts. And so we've taken some data just to compare OBD and QPDI, specifically looking through the lens of PFM, because it exposes the differences quite nicely here. So with PFM, we're applying an AC electric field to the cantilever to apply, we're applying an AC bias to the cantilever to apply an AC field to the sample. And this causes the sample to expand and contract due to the converse piezoelectric effect. And you can see that there. Now we keep track and monitor the resulting cantilever tip displacement or angular changes as measured by the detector. And again, QPDI would give us displacement. And in this case, we see an optical beam detector design scheme here. So it's giving us the angle. And in this particular case, the AC drive voltage going to the cantilever and the response are in sync with one another. So there's zero phase lag between the two signals. And I've represented the polarization vector of the sample as pointing down in this case. But that need not be the case. If in the case where the polarization vector is pointing up, you would have the phase signal be 180 degrees apart between the response and the drive. And then if you have a polarization vector at some different angle, then of course it's the vertical component of that polarization vector that matters for this out-of-plane response. And we simply look at the phase and the amplitude as I've marked there, and we keep track of those signals and plot them as images. And that's essentially how PFM works. One additional bit of information here, a specific PFM technique is to do switching spectroscopy. So we've talked already a little bit about the polarization vector here. Turns out for ferroelectric samples, you can change the polarization by applying a DC bias. So what we do is everything remains the same as you see here. So an AC bias is applied to the cantilever, but on top of that, we apply a DC bias and slowly ramp up the DC bias until we might see a polarization change of the sample. And at that point, that bias voltage, that DC bias voltage is called the coercive bias. So it's the voltage that's needed to switch the polarization of the sample. So we did this switching spectroscopy PFM, SSPFM for short, on a sample that we know to be not ferroelectric. And why did we do this? Well, it turns out that you can actually observe seemingly evidence of a seemingly ferroelectricity if the spot's not positioned properly. So here's the QPDI spot, and it's positioned on the cantilever, not directly over the tip, but in a place here where we can actually measure the cantilever changing due to electrostatics, and we can actually see that electrostatic bending. So when the spot is positioned in this location, as I've shown here, we get a response that looks like a response that's indicative of ferroelectricity, when in fact it's just an artifact. And this is actually what we would see with OBD as well, because of course OBD is sensitive to cantilever slope, and you get that slope change due to the electrostatic interaction between the cantilever beam and the sample. And this is what the reason for the term strange ferroelectrics, which was used to describe samples that seemingly had a ferroelectric response, but should really have no physical basis to be ferroelectric. And it was a mystery for a while, but we now know this is just an artifact. So if we position the QPDI spot properly directly over the probe tip, we get the proper response as shown here in blue. There really should be no observable response on soda-lime glass. Note that the cantilever is still electrostatically bending. We can't stop that from happening, but we can, with the QPDI design and the position of the spot, we can become insensitive to this. We've already seen tip sample friction in a force curve. Here it is as applied to a PFM image. In this case, it's periodically poled lithium niobate, or PPLN for short. And we've imaged here the sample at different scan angles with the same tip and the same image settings, just at different scan angles. And so here's a comparison between the OBD and the Vero QPDI amplitude, again, just at scanning at different scan angles in each of these three images here. And you can see that tip sample friction causes this unintended cantilever bending, just as we saw with the force curve. But now when we apply it to the image, we can see it has real consequences for the OBD amplitude. At 0 degree scan, different from 90 degrees, different from 60 degrees, whereas with Vero QPDI, all of those amplitudes are the same regardless of the scan angle. And that's how it should be. And then, the other way you can have a artifact with forces causing the cantilever to bend and buckle is if the sample has any in-plane response. And so here's a unit cell of bismuth ferrite, or BFO for short. This is oriented, this is 100 BFO sample here. And the polarization vector for the sample has both in-plane and out-of-plane components. And so the polarization vector for BFO starts from the center atom there and emanates out to one of the corner atoms. I'm just going to show the polarization vectors pointing downward because the sample has been pulled in the downward direction. And I've tried to match the color scheme there for each of those polarization vectors with this color scheme that I've chosen to represent the OBD response. So you can see some regions in the OBD image that are yellow. Here are these yellow stripes, and that might correspond to this particular polarization vector, which would cause the cantilever to bend in this way. It's going to pull the tip sort of away from the base of the cantilever and bend the cantilever. Of course, this is greatly exaggerated, but just to show the point that there will be a deflection change at the cantilever that's not corresponding to any out-of-plane component, but simply due to the lateral component of this vector. All four of these vectors have the same vertical component. Just the lateral vector points in different directions. So similarly, you have some regions here on the sample that are sort of these dark blue stripes, and that corresponds to this polarization vector, which might bend the cantilever in this way, and again cause some deflection change, which gets interpreted as real out-of-plane signal, when it's really just this in-plane component of this vector that's causing this deflection to happen. And then you have different regions here, which are sort of this greenish color, and those correspond to the polarization vectors, as I've shown here, which torsionally rotate the cantilever, but don't actually change the vertical deflection of the cantilever. Now, if you do the same measurement with Vero QPDI, again, the spot's positioned directly over the probe tip, and even though this bending still occurs, unless this probe tip moves up or down, Vero is going to see sort of the no signal, and that's what's happening here. This particular samples has the polarization vectors as I've shown here. The vertical component is constant across the entire image, and so we shouldn't see any contrast there. And with OBD, any contrast that we see is actually just the in-plane response cross-coupling in as an artifact into the out-of-plane response. Here's another sample that shows this in-plane PFM response cross-coupling in. This is erbium manganese trioxide, and in this particular case, the grains that have been outlined in red there are, this is a polycrystalline sample, so the grains are oriented randomly, and so the polarization vectors are going to be oriented randomly. So you have some grains that are oriented a little bit more with the polarization vector in plane and some that are more out of plane. The ones that are highlighted in red there are mostly in plane. You can see that because there's very little response in the QPDI image, whereas with the OBD image you can see clearly a lot of response there. And again, this is just an artifact of the in-plane component cross-coupling in. The blue grain here is truly oriented out of plane. You can see the response both in QPDI as well as in OBD. As a side note, this OBD image was taken with this technique called DART, which stands for dual AC resonance tracking. So the resonance tracking is the important part there, which means that it's not a fixed frequency that we're using, but we're actually always varying that frequency to stay on the resonance of that response. Mostly the reason for that is to accentuate the signal, to amplify the signal, and that's becomes necessary. It's one of the strategies common strategies in PFM particularly for these low response materials that have very small piezoelectric coupling coefficients. Where the response is small, you may very well not have enough response to get up above the noise floor. And so with DART, tracking resonance and being on resonance all the time, you can accentuate and amplify that signal. But note that, even though you can see signal, you still have artifacts, right? So not all the signal is actually true. So this is same sample, but this is sort of a nice transition to the second topic here of this webinar is precision. And so again, this erbium manganese trioxide is a low response material. And now instead of using DART as we had in the previous slide, I'm just doing single frequency PFM at 30 kilohertz. So the frequency is fixed, just to match the same as what we did with Vero. You can see the signal sort of beneath the noise there. It's much clearer with Vero QPDI, but the noise floor of OBD is such that it obscures a lot of these low response signals. Now, just as a reminder, we could use DART for this and see the signal again, but you still get the same artifacts that we've been discussing. Another low response material is hafnium oxide, or hafnia for short. You can see here we've again used identical settings between the OBD image and the QPDI image, but you can clearly see the signal contrast in QPDI. But now, this signal response is so low that you don't see any of it in the OBD image. All you see is this white noise of the OBD detector. So the noise floor is essentially quite a bit higher than the actual signal. I should mention that in addition to DART, this resonance tracking technique, another strategy with OBD, if you have a low response material such as hafnia, is to simply use high voltage. The piezoelectric coupling coefficient here that you see we're plotting these images in is in units of meters per volt, right? So if you have a very low response material, you'll have a very low, small dimensional change for a particular voltage. So if you want a larger change in dimension, you just increase the bias voltage, right? But, again, just as with DART, there will be artifacts still. You can't get around that with OBD like you can with QPDI. And in this particular case, I'm calling attention to HV because hafnia is, this is a thin film, and so we have to worry about dielectric breakdown. So we couldn't actually use HV high voltage on this particular sample. The other thing is that the coercive bias is fairly low for hafnia, and so we would be switching the material as we imaged it if we use HV, which is not ideal. Okay, the other way we can talk about precision is simply by looking at a thermal noise plot, which is indicative of the AFM noise floor. So here's the OBD thermal noise plot on a particular cantilever. The resonance is out here at 50, 60 kilohertz. And you can see a little bit of a frequency dependence there on the noise floor, 1 over F. But typically OBD noise floors they are dependent on the cantilever and the spot size, but for a lever like this, typically 200 to 500 femtometers per root hertz or even higher. Now, for very high resolution measurements, we would often choose short cantilevers for lower noise. And the other thing with short cantilevers is the spot better fills up the cantilever, and so that's also affects the noise. It lowers the noise floor. So for short cantilevers, you might expect something like maybe 25, 30 femtometers per root hertz with OBD. With QPDI, there's no dependence on cantilever. It is what it is, and it's dramatically lower, in fact 20 times lower than OBD. You still see the resonance peak there, but now the noise floor has been lowered by 20 times. Again, you see a little bit of a frequency dependence there, but it depends on the operating frequency that you're at. But typical noise floor is somewhere anywhere from 10 to 20 femtometers per root hertz for QPDI. Pretty incredible results, and could have a lot of impact on a lot of different techniques. As a side note, if you take that spot and move it from the tip to the base of the cantilever in QPDI and take another measurement, you get that response shown in red there. And this makes us believe that the Vero QPDI noise floor is low enough for us to see actual, the cantilever's subresonant thermal motion. This is Brownian motion, so pretty incredible there. Okay, I wanted to end with this slide. This is some data I took on aluminum scandium nitride, which compares again QPDI and OBD. What we're looking at is histograms of the piezoelectric coupling coefficient. These all start as piezo response amplitude images on aluminum scandium nitride and then converted into piezoelectric coupling coefficient histograms. And so here's our very first histogram taken with OBD and the corresponding histogram taken with Vero. Same sample, same tip, same settings, just switching out the detector type. Now I use different cantilevers and scan settings for each of the 5 pairs of OBD QPDI images to in part mimic experimental variability. And so at this point, I switched the probe, changed the scan angle, changed the drive amplitude, and then did an OBD image and a QPDI image. And then again, change probe, change scan angle, change drive amplitude, take another OBD image and another Vero image. So within each pair, the scan settings and probe are the same. And I repeated this 5 times, and this is what I got. You can clearly see differences in the histograms of the piezoelectric coupling coefficient between Vero QPDI and OBD. The Vero histograms shown in blue are much more tightly clustered, whereas the OBD histograms shown in red there are much more scattered. Furthermore, you can also see the Vero histograms are much narrower, which speaks to the higher precision and lower noise floor of the QPDI measurement compared to OBD. So with that, we will end the talk of the webinar and open it up to questions. Thanks very much for your attention.
All right, thank you very much for the talk. So we can get right into some questions that have been submitted. So if you have not submitted your questions yet, please feel free to do so. So to start here, I have a question addressed to Jason, and that is it possible to make lateral PFM measurements on Vero?
Yes, absolutely. And we didn't really mention this in the talks, but we have both detector types actually present in the Vero AFM, so you can choose which type you want to use. We recommend, of course, QPDI just for its increased accuracy and precision. But if you wanted to do OBD just like you've always done, that's also an option. So yeah, you can do lateral measurements with OBD. Good question, thank you.
Mm-hmm. Great. So another question for Jason, sorry. What are the main differences between using Vero and a standard Cypher? Is it complicated to set up?
Yeah, actually they're quite similar in setup. Vero has a couple extra hardware toggles to select for whether you're using a silicon or silicon nitride cantilever, plus whether you're working in air or liquid. But apart from that, it acts very much like a Cypher. And in some ways, it's actually quite a bit easier, right? Because with Vero, since we have the interferometer built in, the calibration is a lot simpler.
Thank you. So here's a question for Ben. Is it possible to upgrade an existing Cypher to use QPDI?
Yes, absolutely. So most Cyphers can be upgraded. We can convert them over to Vero. The exceptions are some very old Cyphers, but the vast majority of Cyphers can be upgraded to Vero. It's fairly extensive, of course, because we have to replace the whole cantilever detection optics. Basically, what we call the head needs to be completely swapped out. Some of the electronics need to be upgraded, including the controller. So Vero requires our new ARC3 controller. So Any system that doesn't have that, which would be most of the ciphers out in the field, would also need a controller upgrade. But it's certainly possible. And if you're interested, please contact us and we can let you know what it would take to do it.
Mm-hmm. Thank you. So we've received a few questions about probes. So let me just say them both, and I can address this to Jason. So how to choose tips for Vero versus OBD, and what cantilevers do you use for PFM with QPDI?
Okay, good questions. Yeah. So, with Vero, you can use any probes that you would normally use with OBD for the most part, standard silicon or silicon nitride cantilevers. We prefer for a lot of our measurements to use probes with the tip setback, where the tip isn't out at the very end of the cantilever, but there's a little bit of a setback from the end. And you can probably guess why, to actually position the spot directly over the probe tip. If it's a visible tip cantilever, then you can't, of course, position the spot directly over the tip, although you can get close. Yeah, apart from that, same sort of considerations would apply. We'd probably ideally have a probe with a nice reflex coating so that the signals are strong. Yeah, you can, you can use a variety of spring constants, and you're not limited by that. There are some probes out there that what matters is actually the thickness of the chip that's used in these probes, and there are some probes that are not, the thickness of a silicon chip or a silicon nitride chip, and so those might be incompatible, but those are pretty rare in special cases. Did I answer both questions?
Yeah, I believe
forget
so.
if I answered the second one.
Yeah. So maybe not specifically for PFM. So do you have a specific recommendation for PFM?
Yeah, with PFM, a lot of the measurements that you see in this webinar were taken with an Adama probe. So those were Adama 2.8 probes, and I like them. They're a little bit more pricey than standard cantilevers, but they last a lot longer. They're quite robust. So I actually end up just reusing the same probe over and over again until the probe tip breaks or it's contaminated. But yeah, those are quite nice for robust measurements. But you can use any probe that you've used if you're doing PFM, any probe that you've used in the past with an OBD AFM, whether it's a Cypher or an AFM from one of our competitors. Those metallized probes will work just fine.
Great, thank you. So here's a question addressed to Ben. Can you do standard AFM modes with Vero, such as tapping mode, MFM, KPFM?
Yes, so yeah, we can support all the modes that we support on a Cypher. There are some limitations for Cypher S versus Cypher ES, but essentially anything you can do on a Cypher S, you can do on a Vero S, and anything you can do on a Cypher ES, you can do on a Vero ES. So there are no limitations there. In most cases, you have the choice of using either the OBD signal, as Jason mentions. We have an auxiliary OBD signal available for use. You can use that with modes if you choose to. But as Jason mentioned, we would generally recommend that you use the QPDI signal for all the reasons that we've outlined here today, and it's compatible with almost all of those modes.
Thank you. So another question your way, Ben. Does Vero work in liquid?
Yes. So yeah, I mean, Jay has mentioned you can use pretty much any probe with Vero. So and it is compatible with the same liquid probe holders, liquid cells as the Cypher S and the Cypher ES can be used on the Vero S and Vero ES. Not sure Jason mentioned in his talk, but there are a couple adjustments, hardware adjustments, toggles in the head of the Vero. So we select between air or water operation with one of those toggles, and then we select between the silicon nitride probes, which often have the thicker glass probe chips, or the silicon probes, which typically have somewhat thinner probe chips. But yeah, you set those toggles appropriately, and you can work in air or liquid. You can use silicon or silicon nitride probes.
Thank you. So we can address this question to Ben. So is Vero compatible with large sample systems?
No. So right now, Vero is, by definition, the AFM that we've shown you. So it's clearly based on the Cypher platform. That's what we built on to create Vero. So right now, that's our only platform that includes QPDI is Vero.
Thank you. So a question for Jason. Does the improved sensitivity of QPDI eliminate the need for PFM amplification techniques like DART and high voltage biases?
Yeah, I mean, at least certainly of the samples that we've looked at, you don't need to be on resonance or use high voltage to be able to see the signals. Simply with QPDI's noise floor, we're able to see those low response signals.
Great, thank you. So a question for Ben. Does Vero support the same accessories as Cypher?
Yes. So yeah, we support the same accessories on Vero that we do on the Cypher S and the ES. The one exception, the one thing that we just haven't really gotten around to testing yet is the electrochemistry cell for the Cypher ES. We haven't confirmed that it's compatible with Vero yet because it's quite a bit different in how it all goes together. So that's something that we still need to verify. But otherwise, the sample heater, cooler, humidity cell, all the various modes, and even the optional modes, all of that stuff works on Vero. So so yeah, with very few exceptions, anything you can do on a Cypher, you can do on a Vero, just with a better cantilever sensing mechanism.
Mm-hmm. Great, thank you. So I just got a new question in here. So this can go to most likely Ben, and I'll split it up. It looks like it's two-parter. So is Vero compatible with in situ high temperature measurements? If so, how high of a temperature?
Yeah, so as I mentioned, we can use the Cypher ES environmental control accessories. So with our high temperature heater, we can heat between ambient and 250 degrees C. If we use our heater cooler, we can go from 0 to 120 C, I believe it is.
Mm-hmm.
Both of those are compatible with Vero.
Mm-hmm. Great, thanks. So the second part, they ask, is there possibility to measure pyroelectric coefficient too?
We haven't done any specific work on that. I know that there are some examples in the literature, people studying pyroelectric materials with AFM, but we haven't done any sort of development to develop new techniques for that or anything like that on Vero.
Mm-hmm. Thanks. So here's a question. We touched briefly on being able to measure other modes, but someone asked that this seems specialized in measuring vertical directions. So how does it measure lateral measurements like friction? And I can go to Jason.
Yeah, I mean, again, we can use the OBD detector to do lateral signals. So everything that you could do previously with your OBD AFM, you can do also with Vero. It's just that on top of all that, you have other capabilities and improved, improvements in accuracy and precision for a lot of modes.
Thank you. So another question here for Jason. How do you optimize the position of the blue drive and QPDI lasers on the cantilever?
Yeah, and it's nice because with Vero we still have the option to have blue drive with the previous interferometric AFM that we released, the IDS. that took the place of blue drive, so we didn't have that option. But yeah, you would optimize the blue drive spot just as you normally would. We typically put that on the base of the cantilever and move it around for the largest actuation amplitude. And the QPDI spot, we typically, it sort of depends on what mode you're doing, but these PFM measurements where you really care about the accurate, tip displacement, we typically place the spot directly over the cantilever tip itself, which is why we prefer, cantilevers with a tip set back. And I should say also, there are ways you can fine tune that as well. So you could do, for example, like a force curve, and your sensitivity will be a constant now. So if you move that spot around, you'll get that value when you're directly over, you've positioned the spot directly over the tip.
Thank you for further clarifying. So another question, Jason, why is Vero not influenced by the changing angle of the cantilever?
Yeah, good question. So like in the OBD, that angle is actually redirecting the spots on the photodetector, changing the measured signal. With QPDI, that beam is still changing angle, but there's enough overlap of the incoming or the return beam, so enough signal is getting back. And if you think about how an interferometer works, it's looking at the interference between the reference beam and the sample beam, or the beam from the two beams that we're sending to the cantilever. So long as that happens, you still have a signal. For very large deflections, you might lose a little some signal, but the measurement will still of displacement is still there.
Thank you. So we don't currently have any new questions in. I'll give another 20 seconds or so to see if any pop in here. But if we don't see another question in the near future, then we could likely end it here. So thank you everyone for attending. And again, this webinar will be available online in the near future. So feel free to look out for that. If your questions were not answered, you can also reach out to us and we'll get back to you as soon as possible. So thanks again.
Thank you.
Thanks a lot.